Week number 8 is on alternating current circuits. You should be reading chapter 30. And in this screencast, I want to review or preview the important equations. But really, you will need to use the equations from chapter 30 in the homework assignments. So here's sort of the part 1 of the video on the theory. And the outline will have 4 points. First of all, oscillations in LC circuits. If there's a circuit with inductance L and capacitance C, then there can be oscillations in the circuit. And that's really the basic example of alternating current. And the frequency of the oscillations is 1 over the square root of L times C. Or really, that's the angular frequency. The period is 2 pi divided by omega 0. Omega 0 is 1 over the square root of LC. The second point is damping when there's resistance. So again, we'll have an LC circuit, but in addition, there will be resistance. That also can alternate. That can produce alternating current. The frequency is not 1 over the square root of LC. It's a little bit less. The frequency is the square root of omega 0 squared minus r squared over 2L squared. So it reduces to omega 0 if r is 0, but it'll be a little less than omega 0. More importantly, there'll be exponential decay from the resistance. The resistor dissipates energy. So the oscillations in an LC circuit have constant energy, but the oscillations in an LRC circuit are decreasing because the energy is lost from resistance. Now, part 3 puts in a source of alternating voltage. So these are called driven AC circuits. You have not only inductance, resistance, and capacitance, but you also have EMF. So there'll be an EMF which is sinusoidal in time. Now, that frequency may not be the same as the frequency of the LC circuit by itself, or the LRC circuit. So there'll be a dependence on the frequency of the electromotive force. And there'll be the phenomenon of resonance. When the frequency, the driving frequency, is equal to the natural frequency, when omega is equal to omega 0, or omega r if there's a little bit of resistance, then you'll have the largest currents in the circuit. And that's really important because that's how radio receivers tune on the frequency of an antenna. And the final part is energy. This concerns the voltage, points 1, 2, 3 concern the voltage, the current, the charge on the capacitor. Point 4 is concerned with the energy or power in the circuit. And we already have from previous weeks formulas for energy in a capacitor, energy in an inductor, power dissipated in a resistor. But those are for DC circuits. And what happens in the case of AC circuits? So in orange here we have the most important equations, so be sure you have these written down in your notes. All right, now we're going to start with oscillations in an LC circuit. So we imagine a little circuit, just a one-loop circuit, with a capacitor and an inductor. Of course, there can be more complicated circuits, but this will be the basic effect if we just consider the simplest case. So we have a capacitor, and we'll assume it has some charge. So the capacitor has charge plus Q on one plate, minus Q on the other plate. Then there will be current in this circuit. And the current, well, the current doesn't go through the capacitor because the capacitor has an insulating layer. But the current is directed out of one plate and into the other plate. That's what changes the charge on the plates. Now the current will pass through the inductor because the inductor is nothing but a solenoid. The inductor is just a coil of wire. And we're going to neglect any resistance for now. There could be some resistance in the wire, and that will bring us to the second case of a LC circuit with resistance. But for the ideal case, let's suppose there's no resistance. Now we can analyze this circuit using Kirchhoff's rules. It's just a single loop circuit, so there's just Kirchhoff's loop rule. If we calculate the change in potential around a closed loop, it'll be zero. So let's start at this point and go around the loop in this direction. Oh, by the way, I've assumed that the current is in this direction. The current is directed towards the positive terminal of the capacitor. So positive I will mean a current in this direction. What's that? Counterclockwise. Negative I will mean a current in this direction, clockwise. And of course, the answer is going to be an alternating current. So sometimes the current will be positive and sometimes it will be negative, as the current will alternate back and forth, sometimes clockwise, sometimes counterclockwise. All right, so now we're going to go around the circuit starting at this point in the clockwise direction. So the potential change across the capacitor, if this is plus Q and this is minus Q, is Q over C. Notice that if Q is positive, then the potential change is positive, plus Q over C, because this would be the high potential side. If Q were negative, then the potential change would be negative, because if Q were negative, then this would be the high potential side. All right, so that's delta V across the capacitor. Now we have delta V across the inductor. And we know from last semester, by electromagnetic induction, delta V is L di dt. But what's the sign? L di dt is delta V. That's the definition of inductance. But what's the sign? Well, if the current isn't going in this direction, then the change in the potential across the inductor is plus L di dt. The current is in this direction. the change in potential is positive. Positive meaning clockwise. That's what's called back EMF. It's an EMF in the opposite direction from the current. And that's because of Lenz's law in electromagnetic induction. So we have delta V across C plus delta V across L is 0. Delta V across C is Q over C. Delta V across L is plus L di dt because I've defined positive I as being in this direction. So for example, if I were increasing, then di dt would be positive. Then there'd be a back EMF. It's Lenz's law. It's trying to prevent the change in the flux, in the magnetic flux. So that's Kirchhoff's loop rule. Now we also have a relation between I and Q. I is dq dt, because any current that comes around here has to deposit charge on the positive plate of the capacitor. It can't go through the capacitor because the capacitor has an insulating layer. So the amount of charge per unit time approaching the positive charge, a positive plate of the capacitor, is I. So dq dt is equal to I. And similarly over here, the charge, the current is in this direction, so there's charge, if I is positive, there's positive charge leaving the negative plate, and so the change in potential will be, so the current will be dq dt. Now put together these two equations. I have a differential equation. And if I put these two equations together, well, I have Q over C plus L d squared Q dt squared is 0. Divide both sides of the equation by L. So the second derivative of Q, with respect to time, plus 1 over LC times Q is equal to 0. That's the oscillator equation. That's an equation that you will recognize from mechanics. It's the equation for simple harmonic oscillations. It's just like a mass on a spring. The equation of motion for a mass on a spring is x double dot plus k over m x equals 0, where what I mean by dot is derivative with respect to t. Well, that's simple harmonic oscillations of a mass on a spring. You see, it's the same equation. The position being replaced by the charge on the capacitor. So here's the equation we have to solve. Q double dot, or Q double prime, second derivative of Q, plus 1 over LC times Q, or Q over LC, is equal to 0. Well, a little bit of math background here. For simple harmonic oscillations, say some function f of t is oscillating in time with harmonic oscillations, the differential equation is d squared f dt squared plus omega squared f is equal to 0. The solution to that equation is, it could be cosine omega t, it could be sine omega t, it could be cosine omega t minus some phase angle, or sine omega t minus some phase angle. The basic solution is cosine omega t. And why is that a solution? Because the derivative of the cosine omega t is minus sine omega t times omega by the chain rule. And then the derivative of that is minus omega times cosine omega t times omega by the chain rule. It's minus omega squared cosine omega t. So if I put in here f is cosine omega t, d squared f dt squared is minus omega squared cosine omega t plus omega squared cosine omega t is 0. So for any constant a, this will be a solution because I'll have the constant a in both terms. And for any phase angle phi, this will be a solution. So there are two undetermined constants, a and phi, which will determine the solution of this equation. So that's the most general solution of this equation. It has these two constants, a and phi. Of course, omega is not a constant. Omega is just the variable that's in the equation. Well, it's a constant, but it's not an undetermined constant. It's a determined constant. It's the constant which is in the differential equation. In the case of this equation, omega squared would be 1 over LC. Omega here is called the angular frequency. And the period of oscillation is 2 pi divided by omega. So omega is some number of radians per second. And the period is 2 pi radians, that's a complete oscillation, divided by some number of radians per second. So this will be a time. 2 pi omega is a time. It's the time for one oscillation. That's called the period. It's the period of oscillation. So this is the time for one oscillation, from one maximum Q back to a maximum Q. Or it could be from one minimum Q to the next minimum in Q. Or it could be from this point to this point. Any way you want to define it, the period, capital T, is 2 pi divided by omega. So that's T. Now we have these two undetermined constants, a and phi. A is called the amplitude. So cosine varies between +1 and -1, so f will vary between +a and -a. So here would be a, the maximum value of Q, and here would be -a, the minimum value of Q. And Q will alternate between +a and -a, as cosine alternates between +1 and -1. So that quantity is called the amplitude. Now what about phi? Phi is called the phase angle. It depends on where the oscillation starts at time 0. See, at time 0, f would be a cosine minus phi, same as cosine phi. So this value is a cosine phi times 0. Now, this oscillation could start at a maximum. That would correspond to phi equals 0. Or it could start at a node. That would correspond to phi equals pi over 2. Or it could start at the minimum. That would correspond to phi equals minus pi or plus pi. So the value of the phase angle determines where does the oscillation start at time 0. All right, now A and phi are not determined. They must be determined by boundary conditions. For a time dependence, that would be an initial condition. So for example, maybe you would have A equals 5, and F equals 5 at time 0. Well, that would correspond to A equals 5 and phi equals 0. So, this little shift in the position of the maximum occurs where cosine is equal to 1. Cosine is equal to 1, so omega t is equal to phi, so t is omega over phi. So this little shift is t equals phi over omega. Remember, omega has units of radians per second, so this is radians divided by radians per second. That'll be a certain number of seconds. That'll be a certain time. So we can write Q of t as A, that's the same as Q max, cosine omega 0 t minus phi, where what's omega 0? Well, this part is omega 0. This is omega 0 squared. I'll call that omega 0 squared as opposed to just omega squared, because we'll have other problems where there'll be other frequencies. So omega 0 is the natural frequency. Omega 0 is 1 over the square root LC. Omega 0 squared is 1 over LC. That's the natural frequency. And that's the solution of the problem of the LC circuit. Now, in this circuit, energy is conserved. We know the equations for energy. The energy stored in a capacitor is Q squared over 2C. Remember that from several chapters ago. So if I put in Q max cosine omega 0 t minus phi, it's Q max squared over 2C cosine squared omega 0 t minus phi. So there's the energy stored in the capacitor. It's electric field energy. Remember, the energy in a capacitor, so here's the capacitor. It has charge Q and minus Q, where there's an electric field between the plates. This is the energy of the electric field. And we had that in a previous chapter. As for the inductor, from last week, the energy in an inductor is 1/2 Li squared. Now, I is dq dt, so if I differentiate the cosine, I'll get minus a sine times omega 0 by the chain rule. So I'll have here, when I square it, omega 0 squared Q max, sine squared omega 0 t minus phi. I think I have a mistake here. So here's 1/2 Li squared. I is omega 0 Q max. So I really should have here a factor of Q max. Squared because I had I squared. So this is the energy in the inductor. It's a magnetic field energy, because remember, if you have charge coming into a solenoid, there's a magnetic field inside the solenoid, and the energy, 1/2 Li squared, is equal to that energy of that magnetic field. So this is magnetic field energy. Now I say the energy is conserved. Calculate the total energy, UC plus UL. You see I have Q squared over 2C. Well, here's Q squared L omega 0 squared. But L omega 0 squared is 1 over C. So this is also Q squared over 2C, sine squared. And cosine squared plus sine squared is 1. So the total energy is Q max squared divided by 2C. That's just the maximum energy stored in the capacitor. And at any time, the energy stored in the capacitor will be less than the maximum possible. The energy stored in the inductor will be just enough so that the total energy is again Q squared max over 2C. Or I could write it in terms of the maximum current, because remember 1 over C is L omega 0 squared. So I could place here the 1 over C by L omega 0 squared. Then I'd have 1/2 L omega 0 squared Q max squared. Well, that's I max squared. That's the maximum energy stored in the inductor. So you see what happens in the LC circuit. We have the capacitor and we have the inductor. The total energy is constant, but it's alternating back and forth between the capacitor and the inductor. So sometimes the capacitance has all the energy, and there's no magnetic energy in the inductor. And a half cycle later, or a quarter of a cycle later, I guess, the energy is all in the inductor. So we have also alternating fields. We have an alternating electric field and an alternating magnetic field. But the total energy of the two fields is constant. And that's an example of energy conservation. So conservation of energy is a universal principle. And in the LC circuit, it shows up in the fact that the energy of the capacitor plus the energy of the inductor is constant. So far, we have not included resistance. So let's consider again the LC circuit, but now with some resistance. And I'll just take it to be a series resistor. So I have L, R, and C in series. Now when I apply Kirchhoff's loop rule, I'll have Q over C is the voltage change across the capacitor. Now I have a current in this direction. So if I is positive, there's a current in this direction, and this must be the high potential side, and this must be the low potential side. So the change in potential across the resistor would be plus R times I, the high potential minus the low potential. And then again, I have plus L di dt. So going around the loop in the clockwise direction, the change in potential across the capacitor is Q over C. The change in potential across the resistor is Ri. That will be positive if I is positive. And the change in potential across the inductor is L di dt. So it's just like the equation I had before, but I add in R times I. And again, I have this differential relation between current and charge on a capacitor. I is dq dt. And so if I combine these two equations, I again get, and divide both sides of the equation by L, again I got d squared q dt squared from this term, plus q over LC from this term. But now I have in the additional term, R over L dq dt. So the differential equation has changed a little bit. Now, I can write down a particular solution of that equation, not worry so much as I did before about having the general solution. Not worrying so much about the general solution, let me just write down a particular solution. And let me take a boundary condition that at time 0, the capacitor has no charge. This will solve the equation. Q max, some constant, it turns out to be Q max, e to the minus t over tau, an exponential decrease, cosine omega t. Cosine of something I'll call omega sub r t. Now I'll leave it as an exercise for you, or you can look it up in the textbook by Bauer and Westphal. If you compare this equation and this function, you'll find that it's a solution where tau is 2L over R, and omega sub R, the angular frequency, is the square root of omega 0 squared minus 1 over tau squared. So, because of the resistance, there's a change in the frequency. If R were equal to 0, then I would just have omega sub R would just be omega 0. Because if R were equal to 0, then tau would be infinite, and this 1 over tau would be 0. So I would just have the frequency 1 over the square root of LC. But because of the resistance, there's a small change in the frequency. Now we have this exponential decrease. So what's the time constant for the exponential decrease? We have e to the minus t over tau, and the time constant is tau. Well, tau is 2L over R. Again, if there were no resistance, if R goes to infinity, then tau goes to 0. If R goes to 0, no resistance, R equals 0, then tau goes to infinity, and this becomes just e to the minus 0. So if R goes to infinity, this goes back to 1. E to the minus 0 is 1. And this goes to cosine omega 0t. So I'm back to the case of the ideal LC circuit if R goes to infinity. But for R if R goes to 0, but if R is not equal to 0, then there's a time constant 2L over R. And what we have for the charge on the capacitor is a damped oscillation. We still have the oscillation characteristic, but it's not with constant amplitude. The amplitude is decreasing. In fact, the amplitude is decreasing exponentially as e to the minus t over tau, or e to the minus rt over 2L. Now, what's happening is heating or dissipation of energy. Energy is dissipated in the resistor. As we know, the power dissipated in a resistor is I squared R. Now that's 0 if the resistance is 0, but we're going to have this current flowing, and as it goes through the resistor, it's an alternating current. It's an oscillating current, but whatever it is, positive or negative, it's losing energy at the rate I squared R. And of course, where does that energy go? I mean, after all, the total energy is constant, but not the field energy. The field energy is decreasing. Where's it going? Well, it's going into heating up the material in the resistor. You know, resistor is made out of some material. I don't know, maybe it's got to be a conductor, so it's some kind of metal. But the metal's heating up. So the energy of the fields is being transferred into random molecular motions within the metal. That's transfer of energy by heating. So the field energies are decreasing. The charge on the capacitor is oscillating and decreasing, and that's damping. Okay, now point number 3 is the driven LC circuit or driven AC circuits. This is a separate section in the chapter on AC circuits. There's, in addition to capacitance, resistance, and inductance, there's also an EMF, which is alternating in time. So following in the book, we'll say that the EMF at time t is some amplitude, V max, times sine omega t. So the EMF around the circuit as a function of time is sinusoidal. It has some maximum amplitude. It has some period. It has some frequency. The angular frequency is, or sorry, the angular frequency is omega. So here's the circuit diagram. We have, again, the capacitor, the resistor, the inductor, and now we attach an alternating current generator, a generator of alternating current. So it has a potential difference between the two terminals, which is alternating in time. It's some maximum amplitude sine omega t. So this is in the section of chapter 30 on driven AC circuits. This is equation 8 in chapter 30. Now the Kirchhoff loop rule has 4 terms. We still have the potential difference across the capacitor, the potential difference across the resistor, the potential difference across the inductor, that's just like before, plus the potential difference across the generator, the potential difference between the two terminals on the AC current generator. And that is VEMF. Remember, electromotive force is the same units as potential. It's the potential difference that occurs between the two electrodes or the two terminals of the generator. And Kirchhoff's loop rule says the sum of the changes in potential has to be 0. And we still have this differential relation between current and charge. Any current going to the capacitor charges up the plate. So if we put these equations together, we have, here's d squared q dt squared, divide through by L, so d squared q dt squared plus r over L dq dt plus 1 over LC cubed, that was all like before, is equal to, well, plus or minus, let's not worry about the sign too much, it's equal to V max divided by L sine omega t. I'm not going to worry too much about the sign of this term. So there's the differential equation now. Now AC circuits become more complicated because before we had 0 on the right-hand side of the equation, but now we have a function of time on the right-hand side of the equation. So that's a more involved differential equation. If you've had a course on differential equations, you know how to solve this kind of equation. You have to add a particular solution, and that'll be the steady state solution, which is oscillating. And you have to add to that also a solution of the homogeneous equation. That'll be damped, so those will be the transients. So there's a bit of calculus to go through here to solve this equation. It's not completely solved in the textbook, but the results are given. So what I'll do in the screencast is I'll just show the results. In this problem, we're given L, R, C, Vmax, and omega. So we're given these 5 parameters: inductance, resistance, capacitance, the amplitude of oscillation of the AC generator, and the angular frequency, or the period of oscillation of the generator. That's omega. Omega is called the driving frequency. That's the frequency that the generator supplies. If this were just plugged into a wall socket, omega, well, the period of oscillation, the frequency is 60 cycles per second. So the angular frequency would be 2 pi radians per cycle, times 60 cycles per second. So this would be 2 pi times the frequency, 60 cycles per second, 2 pi radians per second. If this were a standard American wall socket. Now, what we're mainly interested in is the steady state. The steady state is the solution to this equation where all the exponential terms have decreased to zero. So after the transients have decayed, the current will just be an alternating current with the driving frequency. By the way, the driving frequency is not necessarily equal to the natural frequency of the LC circuit. The driving frequency is something that's determined by the network or by the generator. In the steady state oscillations, the current has the same frequency as the generator. That's called the driving frequency. So the current will have some maximum amplitude, call that I max, some phase angle, call that phi, and it'll alternate with the frequency of the generator. So that's one relation. I max is related to V max. They're proportional. The constant of proportionality is called Z, or 1 over Z. V max is I max times Z. Remember, in DC circuits, V is IR. So Z has the same units as resistance. So Z is measured in ohms. It has the same unit as resistance. Its name is impedance. Now, what is Z? Z is the square root of R squared plus XL minus XC squared. If there were just a resistor, Z would be equal to the resistance. But because of the inductance and the capacitance, Z is the square root of R squared plus XL minus XC squared. XL is the impedance of an inductor. It's 1 over omega L. And XC is the impedance of a capacitor. It's omega C. So I'm not going to go through the derivation of this result. You can read through the section on driven AC circuits in Bauer and Westphal. Some of the law and Kappa problems may require that information. They may consider, for example, what if you had a driven RL circuit with no capacitor? Well, then you'd have the impedance for an inductor. Or if you had a driven RC circuit with no inductance, then you would have the impedance of an RC circuit. These are all described in the section of the textbook on AC circuits. And you may need to know some of those things for the law and Kappa problems. But for the general problem with inductance and resistance and capacitance, the impedance is the square root of R squared plus XL minus C squared. You notice that if the if the impedance of the inductor is equal to the impedance of the capacitor, then the impedance of the whole circuit is nothing but the resistance of the resistor. But if these are not equal, then the impedance depends on the frequency. So there's a frequency-dependent kind of impedance or effective resistance. I forgot to write down the equation for phi, but again, you can look up the equation for phi. Phi is, I guess it's the arctangent of XL minus XC over R. Anyway, you may have to know that for some of the lawn kappa problems, so look it up in the book. There's one other thing to discuss about the driven alternating current circuit, and that's the phenomenon of resonance. Let's suppose I make a graph of the current at the maximum amplitude of the alternating current. So here's I max on this axis. As a function of frequency. That's the driving frequency. Now the driving frequency is not necessarily equal to, and in general would not be equal to, the natural frequency. So let's suppose on the frequency axis we put about here the natural frequency. That's omega 0. That's 1 over the square root of LC. That's the natural frequency if the resistance is negligible. The natural frequency if there's resistance is a little bit less. It's a little bit less. That's what I called omega with resistance. But if the resistance is small, these are close together. Now let's plot the amplitude of the current oscillations, that's I max, as a function of omega. You see it's V max over the square root of R squared plus XL minus XC squared. If omega is equal to omega 0, 1 over the square root of LC, then XL and XC are equal. So this would just be V max over R. So that'll be some value up here. Now, if omega is different from omega 0, then XL is not equal to XC, and we have additional impedance due to the inductance and the capacitance. So 1 over Z will be something less than 1, or less than 1 over R. In other words, this will be a decreasing function as omega goes away from omega 0. So if I make a graph of this current as a function of frequency, it has a maximum where XL is equal to XC. That is to say, where omega is equal to omega 0. And then the impedance increases, so the current decreases as omega deviates from omega 0. That's called resonance. The largest effect, the largest current driven in the circuit occurs when the driving frequency is equal to the natural frequency. The same thing happens with a driven mechanical oscillator. It's a maximum of the current in the case of the LC circuit. This is very important because this is the way a radio receiver works. A radio receiver tunes to the frequency of the transmitter, which is the radio station that you're trying to listen to. So if you're trying to listen to a radio station with frequency omega 0, you want to tune the receiver so that the driving frequency is the same as the natural frequency of the receiver. So a radio receiver has a little LC circuit inside with a variable capacitance or possibly a variable inductance. And by varying the capacitance or the inductance, you can vary the impedance. You can vary the impedance until you've reached the right frequency where the impedance of the inductor and the impedance of the capacitor are equal. Then you'll get the maximum current. That will give you the maximum reception. So this is the way radio communication works. Inside the receiver, there's an LC circuit, which is tunable. And if you tune it to the right frequency, the frequency of the radio station, if you tune it to this frequency, all you get is static. Or if you tune it to this frequency, all you get is static. But if you tune it to this frequency, then you'll get the current matching the voltage of the antenna, and you'll be able to hear that radio station. Now the final point is energy and power in AC circuits. And again, there's a separate section on this in chapter 30. We know the electric field energy. It's the energy in the capacitor. It's Q squared over 2C. That comes from the electric field. The energy density of an electric field is 1/2 epsilon 0 E squared. So there's the field energy for the electric field. That's energy density. If you multiply by the by the volume enclosed by the capacitor, you get the energy stored in the capacitor. There's magnetic field energy stored in the inductor. The energy of the inductor is 1/2 Li squared. Now the energy density of a magnetic field is B squared over 2 mu 0. The electric field energy is proportional to E squared. The magnetic field energy is proportional to B squared. And again, if you take the energy density, multiply by the volume of the solenoid, you get the energy in the inductor. Now there's energy dissipated in the resistance. There's energy converted from field energy into heating or internal energy of the molecules that the resistor is made of. And you remember, the power dissipated in resistance is I squared R. Now, of course, all of these energies depend on time because you have an alternating current. So the charge is alternating in time, the current is alternating in time, the power dissipated is alternating in time. So we often will be interested in the average power. So if you calculate the average power, the power integrated over one cycle divided by the time of one cycle gives me the average power during the cycle, will be the RMS value of the current squared times R. So we often are concerned not with the instantaneous power, but with the average power, averaged over a cycle in the alternating current. So that's I squared R, but not the instantaneous current, the root mean square value of the current. It's the mean value of I squared, or the root mean square squared. And finally, the power supplied by the generator is I times V, where V is the voltage of the generator. V is the EMF of the generator. Now again, we're not always interested in the instantaneous power. We might be interested in the mean power, which will be the RMS current times the RMS voltage times the cosine of the phase angle between voltage and current. So this constant cosine phi is sometimes called the power factor. And there'll be some I think there's a problem in the ln kappa assignment where you have to calculate the power supplied to an AC circuit, taking into account the power factor. There's a whole section of this in the textbook. So these equations are all familiar from earlier weeks. The averaging over the alternating circuit, the alternating current, that's something new, but you can read about that in the section on energy and power in AC circuits, chapter 30. So this completes the theory. Now there'll be part 2 of the video, which has some examples, work out some example problems.